Hello, my name is James, and over the last 2 summers, I've been writing an emulator of the Apollo guidance computer from scratch. As a very, very brief summary, the Apollo guidance computer was the computer on board the two Apollo spacecraft that helped us land on the moon in the 1960s and 1970s. And it's something that I've taken a very deep personal interest in over the last year and a half or so. As you might imagine, writing an emulator for it is a time consuming and complicated undertaking because I've never done this before, and even if I had, I don't imagine that would change much. I encountered many different and interesting bugs and problems along the way that I needed to overcome to make things work properly. As for why I'm actually making this video, there's two reasons. The first is that I hope it'll be an interesting dive into my debugging process and personal perspective when it comes to solving problems in the software that I write, particularly since I started this project with basically zero preconceived notions or knowledge about how an emulator should or could be written. Secondly, in the process of fixing the most recent of the bugs in the emulator, I discovered what I believe is a small oversight or bug in MIT's original self-test code. This code was used to verify and check the logic and hardware of the computers as they were being designed, built, and tested, and it went through several revisions over the course of the program. Before I really get delving down into the nitty-gritty here, I do just want to mention that I'm not going to be giving a full and detailed explanation of how every aspect of this computer works. It's very unusual and is a bit different from how some modern computer architectures work. However, I believe if you at least have some basic knowledge about CPU architecture and just the general way that operating systems and computers are designed, I hope that you'll be able to follow along relatively easily. So if not, please feel free to ask comments for clarification. I will try and answer them to the best of my ability, but even my own knowledge of this computer is not necessarily comprehensive enough that I would feel comfortable being able to explain every individual detail or facet of how it works, because I myself am still learning, and this emulator was just a big project I undertook to try and help me and challenge myself to learn more about how this computer works. Anyway, for the proper context on how I discovered this bug, I'm going to start from the beginning by showing you the problem I was encountering that led me down this long rabbit hole of debugging. In order to verify that my emulator is working properly once I've implemented the underlying CPU logic, memory, and other essential hardware, I run the very same self-test core rope software that would have been plugged into the computer back in the 1960s as they were testing it. And once I've passed all of those, I move on to trying more complex software or writing my own. In this case, I'm emulating the earlier Block 1 architecture of the computer, running the software codenamed Sunrise Revision 69. An earlier revision of this software, Sunrise 45, had a more basic self-test that my emulator was already completing successfully, so I moved on to this version because it had a much more thorough suite of tests. Here you can see the DISKey, the display and keyboard, which is the primary interface between the computer and the humans that operate it. In this recording, I'm keying in a sequence of commands and data to manually start the self-test, which for this particular rope needs to be started in a rather unusual way because of how the new tests were added into the codebase. However, once I perform the final command, which should initiate the test, the computer immediately becomes unresponsive. The display doesn't return to the readout, which shows me the test status, and pressing keys doesn't seem to register at all anymore. What's going on? Now, from my past experiences, I know that the most common reason for the computer becoming unresponsive is because it's stuck in some kind of infinite loop. In the real computer, such an infinite loop would be caught by the hardware alarm logic and trigger a forced restart to try and remedy the situation. However, I hadn't yet researched this portion of the computer for the Block 1 system, so any infinite loops or other issues which would normally cause a hardware restart would not cause one. While I could have stopped what I was doing to go implement these features, I decided against it because I didn't want to add any further complexity to the emulator code when I was already going to have to debug this problem either way. Plus, I had already implemented a logging system to help me track down issues with code execution. It might not be the easiest or most efficient way to solve these kinds of problems, for all I know, but due to the way that my emulator is trying to replicate the CPU logic at a rather low level, outputting the emulated processor state and other pertinent information in plain text was the simplest way I could think of to provide this kind of data in a way that I could save and search through. And so far, I've been able to solve every problem I've encountered using it as a primary tool. Additionally, if I ever need more specific or situational info, I can always modify my code to add it to the log text as needed. Anyway, I redirected the standard output of my emulator to a text file and repeated the same steps that I just showed you. Sure enough, the computer stopped responding, just the same. Here's one of the log files that I made during the debugging process. Since the computer ended in an unresponsive state, the fastest way to see what was going on inside its digital brain at the time is to scroll all the way down to the very bottom of the file and inspect the relevant registers and status information to see where the computer was and what it was doing. As an aside, one of the downsides of logging the CPU state in plain text every CPU cycle, although it is very comprehensive, it does make the log files become very large very quickly. This one here that you're looking at is 472 megabytes in size. Fortunately, the nice thing about plain text is that it compresses extremely well. By using 7-zip, I am able to compress this log file from 472 megabytes down to around 560 kilobytes, which is almost 1,000 times smaller. And it's a much more acceptable size for storing. Back on topic though, we're looking at the state of the processor's various registers and status flags, represented in octal notation. At the end of this log, we can see that the computer is executing the transfer control, or TC, instruction repeatedly, which is the AGC's equivalent to a jump instruction. Crucially, the Z and Q registers, which are the program counter and return address respectively, are both identical and aren't changing from instruction to instruction, which means the computer is repeatedly jumping to the location it's already in, a very obvious infinite loop. So now that we've confirmed the computer's stuck in an infinite loop, we need to figure out why. The first thing I usually do is check the location in emulated code that the computer was at while this was happening. Since we know from the log file that the program counter was stuck at 2662 octal, and that register always points to the next location in memory after the current instruction, we need to look for address 2661. This address is located in unbanked fixed memory, meaning we don't need to worry about this bank register here in order to find that code. Here is a listing of Sunrise 69, which is a secondary output produced when you assemble the source code into object code, also known as a binary. The reason we need to actually assemble this code and look at the giant listing as a whole instead of one of the individual code files is because only the assembled listing tells us the absolute memory address of each line of code. I realize that there's a whole lot of information in this file, and it's probably confusing to look at, so let me explain the basics. These left two columns are line numbers, but don't worry about those because they aren't relevant to fixing the problem. This column here is the address in memory that the current line of code or data resides in. This column is the raw octal value which the data or instruction assembles into in the binary, which isn't important in this case. This area is where named labels go, which can be used to represent particularly important or frequently used sections of code or data. This area contains the actual source code that the processor will execute in human-readable form. This final area on the right is for any comments or remarks, which were included in the source code by the original developers, except where otherwise mentioned. So if we look at address 2661, we can see that this piece of code is labeled whimper, and that what it does is jump to itself, an intentional infinite loop. Examining the surrounding code, it appears to be related to error handling. Humorously, this infinite loop is referencing T.S. Eliot's The Hollow Men, where the world ends not with a bang, but with a whimper. Remember how I mentioned that if the computer gets into an infinite loop, there is hardware logic in place that should catch it and cause a restart? That's exactly what this code is counting on. To oversimplify, if a serious, unrecoverable problem occurs in the software, it calls this routine, which saves an error code indicating the particular problem, displays a program alarm warning light, and triggers a hardware-induced restart by causing an infinite loop deliberately. Now that we know the infinite loop is intentional and caused in response to an error occurring elsewhere, let's try and figure out where we were just before this abort routine was called. There's a few ways we might do this, but the simplest, in my mind, is to search for the point in our log file where we first enter this routine and work backwards. To do this, we can simply check for when the Z register, which holds the program counter, is equal to the address of this routine plus 1. With a simple Control F, we can see that it happens here. By looking at the return address in Q, or simply scrolling up to see where the program counter was in the previous instruction, we can see that we came from bank 4, address 6416. Remember, Q contains the calling location plus 1, just like the program counter Z register does. If we search for that in the listing, we find this. The error appears to have been caused by an overflow of the waitlist, which is a core part of the AGC system software. That is definitely a big problem that warrants a full computer restart. But now that we've answered our original question of why we're in an infinite loop, we're left with another. Why did the waitlist overflow? To get to the bottom of this, it helps to understand a bit about how the waitlist works at a basic level. Broadly speaking, the waitlist is a system which you can use to schedule a piece of code, called a task, to occur after a given delay period, while the computer does other things in the meantime. To schedule a task, all you have to do is put the delay value in register A, which is in units of 10 milliseconds, where 1 equals 10 milliseconds, 2 equals 20 milliseconds, and so on. Perform TC waitlist, and then place the complete address of the task code immediately afterward, which will be picked up by the called function. So, since we can see in the listing that the waitlist routine is located at address 2124, we can easily search for places where we schedule a task by simply checking when the program counter shows we're currently at that address, just like we did before to find the infinite loop. Let's start from the bottom, the final time we called this routine, because that's the one that caused the overflow. Before we go chasing down the return address that this call came from, let's check a few of the previous occurrences to see if they're all coming from the same place. And it looks like they are. So let's figure out where that is. A according to Q and bank, we came from address 6357 in bank 6. Remember, this is octal numbering, so there's no 8s or 9s. 6360 minus 1 is 6357. Okay, this code here is in the new self-test routine that we were trying to run. That's a promising sign that we're on the right track, and it means that we definitely did manage to start the routine successfully before things went awry. So, the self-test appears to be scheduling a task in the waitlist, but for some reason the tasks are piling up and overflowing, which probably means that they're not being dealt with on time. So, the self-test appears to be scheduling a task in the waitlist, but for some reason those tasks are piling up and eventually overflowing. So we've seen in our log file just a moment ago that we are definitely using the waitlist to schedule this testing task multiple times. So let's see if our task code is actually being executed properly. The task code is located at task address, which is bank 6, address 6407. However, searching for this is more tricky than other times, because simply searching for places in the log file where the Z register equals 6407 plus 1, which would be 6410, returns mostly false positives. You can see that we have 182 results here, which is way too many. And you can see based on this bar here, this orange area, that the occurrences are happening throughout the entire execution, most of which is before we even start the self-tests. So that can't be right. The reason for this is because that address, 6410, is located in banked fixed memory and ends up occurring quite often in other banks while the code execution simply passes through those locations. And I don't have an easy way to search the bank register and the Z register simultaneously in this log file unless I want to start using regular expressions in the search field, which not every text editor can do, and I certainly don't know how to do. However, what we can do instead is search using the B register, which is the instruction buffer register. A fortunate quirk of the way the AGC instruction set is designed is that TC instructions can also be interpreted as a partial address, not including bank information. So, if we find locations in our log file where the current instruction in B is equal to the task address while the bank register is already correct, we can see any places where the processor is explicitly jumping to our task address because it's being processed by the waitlist routine. This narrows down our search results quite a bit, and from the looks of it, our task is only executing once. That's definitely not right. We saw earlier that we're scheduling this task multiple times as the self-test repeats, so if we only handle one of them, it's no wonder the waitlist overflows. But we still haven't figured out why. To find out, we'll need to delve even deeper into the inner workings of the waitlist and the AGC itself. As I mentioned before, the delays for scheduling waitlist tasks are measured in increments of 10 milliseconds. The reason for this is because of the timing method that the computer uses to trigger them. Since the AGC needs to perform a variety of tasks in real time with high precision to do things like controlling the spacecraft, firing thrusters, landing on the moon, etc., its hardware features dedicated timing circuitry. The part that we're focused on are the hardware timer counters, which in block 1 consist of time 1, time 3, and time 4. Each one of these timers are constantly counting up, one by one, every 10 milliseconds. Whenever the value in a counter overflows, it triggers an interrupt in the processor specifically meant for handling that timer. When a task is scheduled in the waitlist, its delay is subtracted from the maximum positive value that the AGC can represent in a single word of memory. and this value is placed into the time 3 counter, meaning that it will count up for exactly the desired duration before overflowing, triggering an interrupt called T3rupt, and causing the waitlist to execute the scheduled task. To be honest, during my own debugging before making this video, I actually researched and traced the execution of the waitlist in much closer detail to verify that it was, in fact, scheduling tasks, setting the timer value, arranging the lists properly, and then removing the tasks after completion. To make a long story short, it was. And I could verify that other operations the computer used, which relied on waitlist tasks, seemed to work perfectly fine. So what was causing this problem? I then spent several days debugging and verifying that my timing code was working properly, which also turned out to be a dead end. It was at this point that I started digging really deep into how this portion of the self-test code, called rupt check, worked, and examining when the trigger for the waitlist task was coming in. That's when I made several important realizations. 1. The self-test task was being processed later than it was expected to. There was a comment in the source code indicating exactly when it should happen, but based on some searching in the log file, I could see it ended up happening much later. 2. I verified that code execution was reaching the end of this interrupt test, but while normally that would imply that it was succeeding and looping back to the start of the whole test suite for another run, there was a test performed during the scheduled task that could still be failing when it came in late. 3. When attempting to service the scheduled self-test task, the processor was never resuming from its interrupted state that instructed it to process the waitlist in the first place. As a result, future waitlist tasks could never be serviced because the processor can't handle any interrupts while one is still in effect. These discoveries helped me pinpoint the exact problem area: the test performed inside the task. Inside this task, we compare the value of zrupt, the location where we were when the interrupt happened, with the expected location where we wanted the interrupt to come in. If the result doesn't match, something has gone wrong and the test has failed. However, because the interrupt is coming in late, this one final test fails, and the code for dealing with a self-test failure was not designed with the expectation that it could be called while in an interrupt. Specifically, it stores the error code in a designated area in memory, increments an error count value, and jumps to the start of the test suite to restart it from the beginning. This last action, as I mentioned before, is fine unless we're in the middle of an interrupt, which we must be in this final test. In that case, we return to the start of the self-test without ever formally resuming or ending this time 3 interrupt, meaning we will never again be able to service any other interrupts that come in, including further waitlist tasks. And so, since the self-test has started over, it reschedules this task again and again, never to be processed ever, until the waitlist overflows and brings everything to a screeching halt. Now, this might seem like a huge issue and baffling that MIT and NASA never noticed it. However, it's only present, to my knowledge, in these self-tests, and there are also several safeguards in place to mitigate its effects, as I mentioned before. For one, when the waitlist overflows and triggers what should be a hardware restart, that will free the CPU from its interrupt purgatory. But even before that happens, an additional hardware alarm should sense the rupt lock condition, being in an interrupt without resuming for a period of longer than 10 milliseconds. And that would also trigger a restart. Not to mention that this bug can only possibly occur if there is a problem in either the timing circuitry or, as I would discover, flaws in the CPU logic that prevent the self-test from working as it wants to, both of which would have caused other more obvious problems when it came time to test any code that would have actually flown into space or to the moon. Even if this bug was encountered during testing, all it really does is trigger a computer restart when the computer engineers weren't expecting it, which likely would have prompted a proper investigation into the problem. Regarding why my emulator was triggering this oversight in the self-test code, after many hours of searching, it came down to two bugs. First, I was incorrectly handling sign bits to determine how the CCS instruction, count, compare, and skip, should cause execution to branch when there was an overflow condition on the data bus. This meant that the self-test's busy loop, which was meant to delay things long enough until time 3 overflowed and triggered an interrupt, wasn't waiting nearly long enough, and so the interrupt was coming in late. Second, I also had erroneous logic in place that was failing to inhibit interrupts from being processed when there was an overflow condition on the data bus, which meant that after I fixed the first bug and ensured that the code was taking the proper amount of time to wait, the interrupt was now coming in on time, but being handled too early, before it should have been allowed to. With both of these bugs fixed, you can see that my emulator finally performs as it should, and is able to complete the self-tests properly, as indicated by the test success counter in the bottom number on the diski here. However, this made me wonder, was this particular oversight in the self-test code ever caught? And if it was, did they ever change or fix it? This is just one AGC core rope. What about others for Block 1, such as the one used for the uncrewed AS-202 mission, which was the first spaceflight that tested a real Apollo guidance computer in space in a real craft? What about the later uncrewed Block 1 missions, Apollo 4 and 6? Could this bug have possibly even managed to make it all the way into Block 2, the computer model that actually flew with people on board? As it turns out, yes. Here is the reconstructed source code for Corona 261, the software that flew on the AS-202 uncrewed test mission. It features what appears to be almost the exact same code, minus a few small differences for things like the ability to show the bank sum of the code to verify its integrity. Crucially, the parts that we're interested in are unchanged. The task code scheduled by rupt check, and the errors code, which simply restarts the test from the beginning on a failure. Next up is Solarium 55, which was the software flown on Apollo 4 and 6. Much the same story here. The bug is still definitely present. This means that aside from Sunrise Revision 45, which doesn't really count because it doesn't have this more complicated self-test anyway, every piece of Block 1 software that we currently have code for contains this little oversight, which I think is pretty interesting. Even more interesting is these pieces of software here, Aurora 88 and Sundial E. These are the primary test ropes used for checking out Block 2 computers, and they feature a complete and further expanded port of the self-tests seen in Sunrise 69 and later ropes. There's definitely been some serious alterations and changes and restructurings to the tests, but the same general structure is present. And look at that. The task code still looks pretty similar, and it's still jumping off to a generic comparison routine to verify that the interrupt happened when we wanted it to. Ah, this is interesting. They've changed how the self-test routine responds when an error occurs. S-mode is the self-test activation flag, and based on this use of CCS S-mode, depending on the value placed inside it, when the self-test encounters an error, it can stop the self-test and return to an idling state if S-mode was positive, or continue it if the value was set to -0. I can't be sure if this was intentional or not, but if S mode is set to -0, then this will prevent the bug from occurring. Because we resume from right where we left off upon an error, we will return to the task and complete it successfully, resuming from the interrupted state and removing the entry from the waitlist. However, if S mode is any positive value, which is, to my understanding, entirely acceptable for the Block 2 self-test, then although the self-test will be aborted upon a failure, it will still be returning to normal code areas without ever leaving the interrupted state, meaning that we still have the same problem. But that's kind of cool. It means that this oversight, in some capacity at least, managed to survive from when these self-tests were written, sometime in 1964 or 1965, we believe, all the way through 1966 or even 1967, and it was definitely still in use for years after that, since these rope modules were used to perform ground tests on AGCs at Mission Control in Houston, out at the launch site at Cape Kennedy, and back at MIT in Boston. This really makes me wonder if perhaps the bug was either never encountered or, more likely, that it was never enough of a problem to warrant a re-engineering of the self-test code. Although this oversight was undoubtedly made, the engineers and programmers were smart people, and remanufacturing crucial self-test code for any model of the computer would be expensive, time-consuming, and might require recertification of the software by NASA or other groups. If they ever encountered this bug, they could very well have followed a similar debugging path to what I did here and figured the problem out and simply made a note to be aware of this oversight. As mentioned before, a very specific set of other problems with the computer need to be at work in order for this issue to crop up. So perhaps awareness of the issue was all that was necessary to ensure this kind of problem wouldn't be encountered or repeated in other, more important code. And again, I want to be clear that I am only speculating at the implications of what it would mean to fix or not fix this problem. Writing software for the first machine to land humans on the moon is no small task, and there were probably a lot of procedures and guidelines in place that I'm simply not aware of, which may have influenced things. And as we can see with Block 2, there were, intentionally or not, measures put in place that could work around this problem and help identify a timing error without causing a computer restart. I don't think we'll ever know one way or the other, but I personally found this whole journey of discovery fascinating, and I really hope that you did too. Regardless, thank you for watching.